Good morning, class, and welcome to this lesson on magnetism to magnetic force. Today, we will be able to identify all the variables to solve for magnetic force. Okay, so um, magnets magnets exert a force on a moving charge, and the key word here is moving. Magnets exert a force on a moving charge. Okay, and they only exert a, this is number one, and number two, they will only exert a force, they will only exert a force if the direction of movement, if the direction of movement is perpendicular or has a component perpendicular to the, to the field. Okay, so magnets exert a force on a moving charge. Okay, only if it's moving. If it's stationary, it does not exert any force at all. And it's only going to exert a force if the direction of the movement has a component that is perpendicular to the field. This is probably going to be the most difficult video I have to make, simply because I have a 2D whiteboard here, and I cannot show my hand in 3D on the video. So this picture right here is going to be the best we have to do here. Okay, so this leads us to a very simple rule. It's called right hand rule number one. So we have our right hand rule number one. And right hand rule number one says this, that if we use our right hand, and when you're taking a test, you are literally going to be taking your hand and turning it upside and down and trying to figure it out. Take your right hand, and if you use your right hand, the magnetic field, which is, we use the symbol capital B for, capital B, the magnetic field B, which is a vector, by the way, magnetic fields have a direction. Your thumb, I'm sorry, the magnetic field is your fingers, your four fingers. The velocity of the charge, okay, also giving us a direction, is going to be, which is V, is going to be your thumb. Okay? And the force exerted by the magnetic field is going to be your palm. So if you take your right hand and put it in front of you right now, you have your, if you put your right hand in front of you so that the back of your hand is facing you, your fingers are pointing up. Your fingers are pointing up. That would be like the y-axis. Your thumb is pointing to the left. That would be the x-axis, and your palm is facing away from you. That would be the z-axis. So we're doing all 3D axes right here, okay? This applies, the right hand rule number one applies. This works for a positive charge. A positive charge. So if we have a negative charge, the force will be opposite. Or essentially, if we have a negative charge, we can call it the left-hand rule. Okay, no one ever says that, but it is what it is. If the force is going up this way, if our field is still going to the right, and our thumb and the velocity of the charge is still out this way, and it's a negative charge, that means it's going to be opposite, meaning it's going to be pointing down the other way. So it's the same thing as doing your left hand, okay? So for a positive charge, the force is going to be exerted against the palm. Okay? Which gives us this new equation. B, which is our magnetic field, equals the force over the absolute value of the charge, okay, V sine theta. So we have our F, we have our V, we have our charge here, and we have our B, okay? So the units for this is going to be the Newton, second Coulomb meter, which is very big, also known as the Tesla. Also known as the, misspelled that, Tesla. Okay, so magnetic fields are measured in Teslas. Okay, so we have our magnetic field, we have our equation here. Looking at our picture again, the angle sine theta comes from the angle between the direction of the moving charge and the magnetic field. The direction of the moving charge and the magnetic field. If V and B are 90 degrees, if V and B are 90 degrees, okay, the sine of theta, the sine of 90 would just be 1. So this simplifies into just that. Okay? And if the direction of the moving charge and the magnetic field have no angle in between them, or theta is equal to 0 degrees, then the sine of 0 is equal to 0, which is why we, in our first page, said that I erased it. Is why we said that the direction of the charge has to have some component that's perpendicular to the field. Even if it's B and it's V like this, and it's only a 10-degree difference right here, there's still a component that's perpendicular. This component right here is perpendicular, and this side right here is the sine of 10 times V sine theta from the equation. Okay? So some component has to be perpendicular to the magnetic field to exert a force. Okay? So magnetic fields are a little bit different than electrical fields. The first picture you see up here, this is a parallel plate capacitor. This is a capacitor. Capacitors exert an electric field. Okay? And so the electric field is pointing from one plate to the other. So if we send a charge in this electric field, it would be pushed along this path into the other plate. Now what I challenge you to do is, this is two magnets. There's a magnetic field in between the north and south pole right here. Take your hand and point your thumb along this axis right here, kind of in the same direction as Q. Point your thumb along that direction. Point your fingers, point your fingers from north to south, so this direction right here. Okay, so this is like my X and Y axis laying down, and what you find using your right hand, that your palm will be facing upward, so it's like your Z axis right here. Okay, so we have all three axes with the magnetic fields. Okay, so a magnetic field is similar to an electric field, but it's going to push a charge in a different direction, a direction that's 90 degrees compared to the electric field. Okay, so that's just the equation. That's just me explaining what each part of the equation is. I'm just going to give you one more tip here. A lot of times, because we do work on paper, and a paper is 2D, we have two-dimensional paper. And so a lot of times we'll say, okay, let's say the magnetic field is going into the page. Let's say the lines are going into the page. So that means we have the arrow method. So think of an arrow. An arrow has a tip, and it has the feathers on the back of the arrow making the X on the back. So if the arrow was pointing away from us, we would see the feathers. We would see the X. So this would be an example of a magnetic field going into the page. This would be an example of a magnetic field coming out of the page. So let's imagine a positive test charge moving into this magnetic field. Use the right hand rule. The magnetic field is going to be our fingers. So you would point your fingers into the page here. Okay, you would point it into the page. The velocity is going to be this way. That's going to be our thumb. So if you point your fingers into the screen right now and turn your thumb to the right here, which direction is this positive charge going to be pushed? Which direction is the force going to be? And your palm is going to face upward along this axis, and the force is going to be that way. Okay. Similarly, if we have a positive charge coming into the field here, these are all dots. Okay, these are all dots. So this is the magnetic field coming out towards us. This charge is still moving from left to right, so the V is going to be this way. Take your fingers, point them out towards your face, coming towards you, out of the page. Take your thumb, point it to the right here, point it to the right. Which direction is your palm facing? Your palm is facing down. Your palm is facing down. So that means the force would push this down along this y-axis right here, along the page. This y-axis along the page. And if we had negative charges, it would just be the opposite. If we had negative charges, it would just be the opposite. Okay, left-hand rule. So that's just the basics for setting up the equation, the basics of what the magnetic field equation is and how to start looking at equations. And like I said before, as you do these problems, get used to it. You're going to be sitting there with your right hand and you're going to be making all kinds of gestures, trying to figure out which direction stuff is going. It's very typical. Don't worry about it.